Facebook's database, but it's still pretty large. And latency has to be low enough because we have large cache in front of MySQL, but if cache misses, then queries are coming to MySQL. Then if MySQL serving query is slow, then it suffers people's experiences on Facebook, which is pretty bad. So Facebook, the MySQL database has to be fast enough for the main database, and our operations are automated. So hardware types, so we use flash SSDs on our hardwares, and it's pretty space bound. So this is the biggest motivation why we started MyRocks project. And it's pretty much space bound. So CPU usage is pretty moderate. So it's not that CPU bound, especially on threads. So these are the basic background. So we are in the process of migrating MyRocks. So MyRocks migration, sorry, the fonts are broken in this laptop, but technical challenges. So initial migrations, at the initial migrations, we need to find out the optimal MyRocks, the RocksDB's current family options. And we needed to create MyRocks instance without downtime because there are already production services deployed with InnoDB. So we needed to deploy MyRocks without stopping existing services. And creating MyRocks tables within short period of time is needed because our database is petabytes. So if it takes a long time to just migrate to 1 gigabyte, then it will take years to migrate to MyRocks, which is not realistic. And another important point of the MyRocks requirement is we don't lose data, or don't return wrong results to the client. So how to verify that? So verifying data consistency between existing InnoDB and the new MyRocks. So this verification was pretty important. And after deploying it, so continuously monitor the resource usages like space or the IOs or CPU memory or query plans, but query execution plans or stores or crashes. So this monitoring was pretty important. So another challenge is so when running MyRocks on master side, so we started migrating MyRocks on slave side, but master was also challenging. So we require using row-based final log for MyRocks. So it's same as MySQL cluster or other storage engines, because statement-based final log needs gap log or table level log like MyISAM or InnoDB. So we don't support gap log feature in MyRocks. So that's why we need RBR. And so removing queries relying on InnoDB gap log was also needed. So there are not many queries like that. But for example, when people want to create the queues on top of InnoDB, then this means you rely on the InnoDB's gap log. So this can't be used in MyRocks. And we recently supported the XA, the two-phase commit support in MyRocks, which is two-phase between binary log and MyRocks. So this is pretty critical for supporting masters. So creating MyRocks instances without downtime. So this was the first requirement. But this is relatively trivial in MySQL. Just picking up bounds the InnoDB slave, then stop slave, then dumping with MySQL dump, then loading into MyRocks. So this is the basic step of using converting to MyRocks, the one instance. So thanks to MySQL, the robust replication support, the stopping one slave does not affect services. So our MySQL replication environment is relatively simple. So it's using a single master and multiple slaves. We don't use chained multi-tier replication environment because it is a bit too hard for us to manage. So another interesting feature is so we use binary log compression during a network. So because we have a geographically distributed MySQL replication environment, so the reducing a network size during a transferring from a master to slaves is pretty important to reduce network size. So, but the dump thread currently is not that efficient. So dump thread compresses binary log with zlib, then sending to the threads. But this happens to all of the for the threads. So if there are 10 threads, then the dump thread needs to compress the same binary code, so for 10 times for all threads. So this is pretty inefficient. And the zlib compression uses a lot of CPUs. So currently, we have a CPU usage issue on the master side. So we are working in progress to switch to a Z standard, which is a newer and a much more CPU efficient compression format to save the CPU usage on the binlog dump thread. And we use semi-sync replication. So we use lossless semi-sync to prevent data loss on the during failover. And we have multiple databases within the instance. So create database. So we have multiple databases, and we use multi-threaded thread on the thread side to reduce the network lag. But hopefully, so the single master and multiple threads only matters for MyRocks. So others are pretty much independent from storage engines. So just stopping one thread, then dump, then load to MyRocks. So the second point is MyRocks tables with optimal column family options. So the RocksDB, as Mark said, there are lots of parameters for RocksDB. So this means MyRocks has lots of parameters, and most parameters are dependent on the column family. So the MyRocks has two important features concerning about column family options. The one is index ordering. So Facebook has you can support like a Facebook newsfeed. So this is fetched by order by time descending. So most of the Facebook workload is range scan workload is descending scans. So this means descending scan has to be fast enough for RocksDB. So by default, the RocksDB's scan ordering is pretty optimized for ascending scans. So we needed a different format. So another format optimized for descending scans. So we call this as a reverse order column family. So reverse order column family specifies the data is stored in opposite order, which means it's pretty optimized for descending scans. And Bloom filter is efficient for makes the point lookups or range scan with equal predicates fast enough. So the Bloom filter needs to specify Bloom filter length, which is highly dependent on the index size. So this means if you have many different types of indexes, then you will need to configure different Bloom filter options, which means you need more Bloom filter column families. So we are still working in progress to make this more robust and more efficient for specifying Bloom filters for column families. But anyway, so the most MyRocks configuration options are per column family, and each MyRocks index belongs to a specified column family. So in production, so we classified indexes on our main database for limited number of similar column family types, like a node or link in reverse order or others. So we have relatively limited a few column families, then mapping many indexes into one of these four column families. So data loading. So we implemented a bulk loading feature in MyRocks to make initial migration from InnoDB to MyRocks faster. So directly creating, so by default, the RocksDB's write path is writing to mem table, then many compactions happens to, and eventually writing to the bottommost levels. So which requires writing the thing, for example, 1 megabyte write results in more like 10 megabytes writes. It's still efficient than InnoDB, but still writing much, many more than original data. So we implemented a bulk loading feature in MyRocks, which creates the data files in the bottommost level directly on insert. So which means bypassing all mem table writes and compactions. So primary key can be controlled by session variable called RocksDB bulk load, which by specifying that options, then everything is written directly. But loading data must be pre-sorted by primary keys. So this is a requirement. But for initial migration, it doesn't matter because we use MySQL dump --order by primary. then it guarantees that the data, original data was sorted by primary key. And for secondary keys, so we added first index creation. So the table at the index, create index, automatically uses bulk loading for the secondary keys. So this is basic data migration steps for us. So create table with no data from MySQL dump, then creating MyRocks tables, then for the table drop indexes because to use a first index creation. Then MySQL dump, then host equal inDB, then pipe the MySQL, then init command set MySQL login equals 0 and set logsil bulk load equals 0. Sorry, 1. So this is a typo. So logsil bulk load equals 1. Then all the table at the index, then using a first index creation. Then after finishing that, start slave. So we on our hardware, so we could migrate about 1 terabyte inDB instances in just 1 or 1.5 hours, so which is pretty good from a migration performance point of view. So the data loading, aside from data loading, so another very critical requirement for us was we don't return the wrong results to clients. So the data verification. So MyRocks is relatively new database technology, so not just us, so many people like you might care about the quality. So they might have more bugs than robust inDB. So inDB is robust. It has over 10 years of history, but the RocksDB is fairly new. So people care about the bugs. So data consistency is one of the most important requirements generally, not just us, but from our communities. So we wrote a verification test tool to check the data consistency between inDB and RocksDB, or just single the MyRocks data consistencies. So we have a couple of tests. So one is an index count check between primary key and secondary keys. So this is the counting the mismatch. If there are mismatches between the primary key and secondary key count, row counts for the same table, then this is something wrong, right? So this is a basic check test, and it doesn't need inDB. So just running a statement like this, so select count from a fourth index primary union, the select count from a fourth index the secondary key. Then this is the same transaction scope statements. So the row count has to be the same. If the row count is different, then the data is broken, so have to investigate. So we started using the tool for and checked all tables with secondary keys. Then and we fixed most of the outstanding issues before deploying in production. The second part is index the statistics. So the checking the estimated row counts, like a show table status. If it's far different from actual row counts, then it's wrong. So this, the funny thing is, this found a bug that the bulk loading didn't update statistics. So that was a bug. So the show table status returned a 0 row count for 1 billion table. So 1 billion tables with 1 billion records. So hopefully this tool detected the problem before deploying in production. And the third part is checksum test with inDB. So comparing between inDB instance and MyRocks instance. So this is needs a bit tricky scripting. So basically what we did was running a start transaction with consistent snapshot with the same GTID positions between inDB and MyRocks instance. Then getting the stopping slaves, then finding the GTID position, then starting transaction with the same GTID snapshot, then running the same queries, same table scans. Then the result has to be consistent. So by running a queries, then comparing checksums. And shadow correctness check is another important feature for us. But so let me check about shadow test. So we have a shadow test framework. So capturing read and write queries from production instances, then deploying them into a shadow, a test master or slave instances. So we have a custom audit plugins to capture capture queries, then we have a logging framework called Scribe, then the capturing queries, then storing into the data warehouse, then deploying them into shadow queries on the shadow instances. And we did that as a shadow master test before deploying master instances. So detecting client errors or finding queries relying on gap log. So we have several commands to list up queries relying on gap log, then fix them before deploying in production. So notable issues and how we fixed was lots of snapshot conflict errors, which is, so MyRocks transaction implementation, so is the isolation implementation is a bit different from InnoDB. So MyRocks implementation is pretty close to Postgres style. And by default, isolation is repeatable read. Then Postgres and MyRocks style repeatable read may return errors called a snapshot conflict errors, where the InnoDB is silently updating the conflict. So it means users may get more errors, and they, So we noticed that, and we decided to switch to read committed for the major queries. Then read committed fixed the problem. And another interesting issue we found was slave stopped with IO errors on reads. So this silently stopping slaves, and it may take time for our automation tool to detect that. So we switched to make the MyRocks abort on critical IO errors from storages from both reads and writes. And index statistics was, as I said before, so inaccurate row counts on bulk loading, so we fixed that. And we are still working in progress about index cardinality statistics has not been as accurate as InnoDB, so we are working in progress in optimizing that. So we currently are worked around to setting the EQ cont index dive limit. So this is the MySQL parameter from 5.6 to 0. So to using index dive to estimate the statistics. And we fixed some crash bugs in MyRocks sandbox. And compaction stores is heavy writes. So this has we often seen in production. So heavy writes causing lots of compactions, which may cause stalls. So we observe stalls on schema changes. So we use online schema change tool. So it's a bit different from GitHub's the Ghost, but we have the schema change tool. So it's basically recreating tables on schema change. And recreating tables, so previously it load too much to memory table and cause too many compactions, which stored replications for about 10 seconds, even though it's called the online schema change tool. So we added the bulk loading feature and the fast index creations feature, and we made our online schema change tool to use them to avoid compactions. And we also used different compression algorithms for RocksDB's levels. So RocksDB has multiple levels, and about 90% of data is stored in the bottommost level.